Hello and welcome to another lesson in the Designing VMware Infrastructure video training series. In this lesson, we're going to be discussing defining virtual machine or VM attributes. In this lesson, we'll start out by looking at how we fit VM configuration into the design and also discuss why it's necessary to put VM configuration into the design. From there, we'll look at three specific areas of VM configuration that I want to discuss with you. First, allocating resources to VMs. Next, configuring VMs for availability. And third, deploying VMs. We'll wrap up this lesson with a look at design impact by examining some design decisions in other areas that will impact your VM configuration, and look at some VM configuration directives that will need to be accounted for in other areas of the design. If you're ready, let's get started. It may seem obvious, but it's important to state nevertheless that the configuration of your VMs will have a direct impact on your overall vSphere design. The design has to take VM configuration into account. Otherwise, you'll find yourself with a design that can't accommodate some of the features that VMs might need. For example, if the VMs are going to use raw device mappings, or RDMs, does your design account for that? Perhaps your design specifies that you're going to use the NFS protocol, in which case you can't use RDMs. And if you have applications in your VMs, either applications that exist in the current environment or applications that you are going to deploy that for whatever reason require RDMs, well, now you've got a problem. Your design can't account for the need that the VMs have. If your VMs have multiple virtual CPUs, does your design account for that? If your VMs are going to use hot plug functionality, does your design account for that? Specifically regarding those last two examples, if you're planning on using multiple vCPUs or hot plug functionality, then you're going to have a problem if you've also specified that you're going to use vSphere fault tolerance to help provide availability for virtual machines configured in this way. So as you can see, there's a direct correlation between VM configuration and the rest of the design and VM configuration. This is yet another example of the holistic nature of the design, in where all of these areas are so closely interrelated that they cannot be discussed independently of one another. So it's important that you craft your design and keep a VM configuration in mind. If you craft your design without accounting for VM configuration, you're ignoring a major influence on the design. And this is why we discuss workload assessment in another lesson in this course. Workload assessment provides a valuable insight into the VM configuration needs. And when I say workload assessment, we're talking about either running an assessment of your existing environment using a tool like VMware Capacity Planner or similar, or an analysis of what the workloads are going to be that you anticipate deploying into a new environment. The importance of the workload assessment and the visibility or insight that it gives you into what the VMs are going to need is critical in looking at the overall design and what it needs to have, what it needs to account for, and the features and functions that it needs to provide to the VMs. With that context set in terms of how VM configuration fits into the design and why it's a necessary piece here, let's move into our first discussion of allocating resources to virtual machines. When we talk about allocating resources to VMs, there are a number of different resources that we'll have to discuss here. Ones that jump to mind immediately, of course, are going to be virtual CPUs and virtual RAM. And the amount or number of virtual RAM and virtual CPUs that you allocate to VMs are obviously going to be very important to the overall design. And some of these reasons might be fairly straightforward, but let's make sure that we have a clear understanding here. Naturally, the more virtual RAM and the more virtual CPUs you allocate to VMs, you're going to affect the design's overall scalability. So if you haven't accounted for the allocation of virtual CPUs and virtual RAM to VMs in designing the overall sizing of the environment and how it's going to scale, then you've got a potential problem here. We've got a conflict that we have to address. The amount of VRAM that you allocate is also going to affect licensing. As you're aware, VMware's licensing offers VRAM entitlements up to a certain amount of allocated virtual RAM, and so how we allocate virtual RAM to VMs will have an impact on licensing. Feature compatibility is another area that could be affected depending on how many virtual CPUs or how much virtual RAM is being allocated. So you'll want to understand that if you allocate a certain number of virtual CPUs or a certain amount of virtual RAM, you may be affecting how other features might work. And of course, there's going to be a direct performance impact on the design. If you are over allocating virtual CPUs to workloads that do not need them, then you may have a negative performance impact, which would not, of course, be a desirable thing. As I mentioned just a moment ago, data from an assessment of the workloads, either current workloads that will be transferred into the environment or the anticipated workloads that you're going to deploy, can help you with right-sizing your VMs with regards to the amount of virtual CPUs and the amount of virtual RAM you will allocate. If you fail to right-size the VMs, then you could cause the design to fail to meet the functional requirements with regards to scalability, potential growth, or performance. And so it's very important that you use the data from the workload assessment to right-size VMs and to establish reasonable amounts of virtual CPUs and virtual RAM based on the needs of the applications and or operating systems running in the virtual machines. In addition to virtual CPUs and virtual RAM, we also need to discuss storage, which is another significant consideration. Storage is a resource that is or should be considered in multiple dimensions. Two of these dimensions, capacity as in gigabytes or terabytes, and IOPS as in the number of operations per second, you have to directly consider in the creation of the storage design. So I will refer you to the lessons on a logical storage design and a physical storage design to see how those factors play in there. But how you go about allocating both capacity and IOPS to VMs is equally important. For example, are you going to use VMDKs or are you going to use RDMs? As I mentioned earlier in this lesson, the use of RDMs requires a block storage protocol, so you cannot use NFS. That is obviously a key driver in the overall storage design. So you'll want to make sure that you understand what your VMs are going to need when you start looking at your physical storage design. Whether you're going to use physical or virtual mode RDMs will also be a consideration because this will have some impact on feature compatibility. The size of VMDKs are going to be something you're going to want to consider as well, because the size of the VMDKs will play a role in the sizing of your data stores, which will play a role in how you allocate disks or storage pools in the storage design. In addition, you must also consider the upper level of the VMDK size at 2 terabytes minus 512 bytes, because you may have workloads that need more than that. So how are you going to address that if that is the case? VMDK placement to account for things like performance or capacity, RPO, RTO, or SLA. For example, if you are creating a design in which you're going to be using replication and site recovery manager, then VMDK placement is very important because you have to make sure that you place VMDKs that have similar RPO, RTO characteristics on data stores that provide that via replication. Performance via IOPS or throughput is another consideration. Capacity is fairly straightforward, but it is something you want to consider. Obviously, you could use something like storage DRS here to help with some of these, but again, that's an example of how a VM configuration aspect, VMDK placement, and VMDK sizing will affect other parts of the design. Finally, you'll want to look at whether you will or need to use or will be using guest OS features like software RAID or a logical volume manager. This might go back to our discussion around the size of VMDKs. If you have a workload that needs more than a single VMDK can offer, but you need that presented as a single logical volume, then you may need to use an LVM within the guest to create a single logical volume at the guest OS layer, which is represented by multiple VMDKs underneath that. Again, this is something that we have to consider and incorporate into design, understand the impact of these things on the rest of the design and make sure that's accounted for. It's important to keep in mind, though, that it's not just about virtual CPUs or virtual RAM or storage. Other resources that we allocate to VMs are also very important. So consider things like the virtual network interface controllers or VNICs that you're going to use. Certain types offer certain advantages. Certain types have different compatibility matrices. Some operating systems are compatible with some and not with others. So these are all things you're going to want to keep in mind. There are also some feature compatibility things to consider as well, that certain features within vSphere may only work with certain controllers. Virtual SCSI controllers is another one. One of the primary drivers here would be guest OS support. So are you going to use the bus logic, the older bus logic parallel SCSI? You're going to use the newer LSI logic parallel SCSI or the LSI logic SAS controllers. Where does the para-virtualized SCSI controller fit in, and for what workloads should it be used? These are all things you have to keep in mind. Are you going to need parallel or serial ports, USB controllers? Do any of your workloads need 3D video support? Each of these resources is going to have an impact on the overall design, and you're going to want to make sure that you understand what the resources are that VMs are going to need so that you can account for the impact of those resources on the design as you craft the design. This reinforces the need to make sure that you have the end in mind when you start, So when you start creating your design, you're going to want to be looking towards the end of what sort of VMs and what sort of resources need to be allocated to these VMs so that you can account for that from the very beginning. Availability is another aspect of configuring VMs or defining VM attributes that we also need to consider. So we have to ask ourselves the questions like, are the VMs configured to support the various availability solutions that we're going to use? vSphere HA we could consider to be low impact with regard to VM configuration. There aren't a whole lot of dependencies and things that you can't do within a VM that would make it unable to be protected by vSphere HA. On the other side of the spectrum, though, we have vSphere FT, which has extensive incompatibilities. So things like virtual SMP or multiple virtual CPUs not supported. Physical mode RDMs not supported. USB or sound devices not supported. 3D video not supported. Hardware level things like extended page tables or rapid virtualization indexing, which are Intel and AMD respectively. Features to accelerate performance not supported. Parallel serial ports not supported. So these are all things that we have to keep in mind if we're going to deploy FT. If you need those features within a particular VM, then you're not going to be able to use FT. Then you need to look for another availability solution. Perhaps guest OS level clustering is something that you need, but with each type of guest OS level clustering, we have some specific configuration requirements. So if you were going to deploy something like Windows failover clustering, there's a very specific configuration that is required for that, and you want to make sure that those specific configuration requirements can be satisfied by the design. The other availability aspect to look at here is whether or not we've provided availability in all available areas. So have we provided host/compute availability, which we would typically achieve through something like vSphere HA or vSphere FT? Have we provided network availability? This is typically accomplished through the use of multiple uplinks out of a virtual switch to multiple physical switches. Note here that in the vast majority of cases, I won't say all cases because invariably there is an exception to the rule, but in the vast majority of cases, there is absolutely no need to look at network teaming inside the guest because we can provide that redundancy at the hypervisor level. Have we provided the appropriate level of storage availability? While most shared storage solutions are highly available with redundant controllers and redundant paths and redundant ports and so on and so forth, is there a higher level of availability required, and how would we provide that higher level of availability? Are we providing the appropriate level of application availability? All of these are driven by the design factors. So the design factors will tell you what levels of network availability you need within a VM, what levels of storage availability you need within a VM, what levels of application availability you need within a VM, and that will help you drive what the VMs need, which in turn will help you understand what the design has to provide and accommodate. VM deployment is another area that you're going to want to make sure you address in the design. As we look at how we go about defining VM attributes and creating VMs, how are we going to deploy those VMs? So your design needs to address the use of templates. It needs to address whether or not there are going to be standard VM configurations. You might think of this as something like a service catalog. And what is going to be included in those standard VM configurations? How much virtual RAM? How many virtual CPUs? What sort of virtual SCSI controller? What sort of virtual NICs? Parallel ports, floppy drives, serial ports, USB controllers, all the various things that you want to know. You'll want to provide at least some base level of standard configurations, and then you can extend from there. You'll also want to look at guest OS customization specifications and include a description of how we would go about customizing an OS, whether it be Windows or Linux, to provide this sort of standard deployment. And one other thing you're going to want to consider is how you go about updating templates. If you've specified that templates are going to be created, how are those templates going to be updated, especially when it comes to security updates? How will you update those templates to accommodate for security updates? There is a potential security risk if you have a template that has not been updated and it's now you take that template and you clone a VM and deploy that. Well, now you've got a VM that doesn't have the latest updates. How are we going to address that? Is that a concern? How do we mitigate that concern? Those sorts of things. Before we close out the lesson, I do want to take some time to reinforce our holistic view of the design by discussing design impact. I'm using a table here. This is a technique that I've used in other lessons in this course. And I have on the leftmost column some design decisions, a first level design impact, immediately to the right of that, and then on the far right, a list of risks that could potentially be introduced by this design decision. And what I've tried to do here is mix it up, not only have decisions that affect VMs directly, although everything will affect the VMs, but some decisions are VM centric, other decisions are perhaps storage or networking centric, and I want to show how they can impact the design. So if we look at the first one, we talk about NFS being the storage protocol of choice. Well, then the natural impact from that is going to be that VMs are not going to be able to use raw device mappings, only VMDKs. Now, we could, as I've explained to you in other lessons in the course where I've used the table technique, we could extend this to show a second level design impact, which says if we're only able to use VMDKs, well, then we're going to be bound to 2 terabytes roughly in terms of being able to present that to a VM. And if a application needs more than that, then we will be required to move into something like a software RAID or guest OS based logical volume manager in order to be able to address the need for that. One risk that this introduces, depending on what OS we're talking about here, that certain OS level clustering configurations won't work because they do require RDMs. And if we standardize on NFS, then we've prevented ourselves or precluded ourselves from using these OS level clustering solutions. Moving down the list, if we decide we're going to by default provision all our VMs with 2 virtual CPUs, well, then we've just closed ourselves out of using vSphere FT because vSphere FT is limited currently to 1 virtual CPU. And so as a risk, we might find that design may not be able to satisfy the availability requirements. That would be a potential problem. Continuing on, looking at the next one, initial VM storage placement will be handled by storage DRS. This is where I was discussing VMDK placement. Perhaps you're going to use storage DRS and may or may not be using storage profiles in conjunction with that to do initial VM storage placement. Well, storage DRS requires that data stores have only a single extent. So that means that any multi-extent data stores cannot be used in this design because they would violate that design decision. That could in turn involve migrations of some sort from multi-extent data stores to single-extent data stores, something of that nature. If we look at using array-based replication and SRM to provide DR protection, then we know one impact out of that is going to be that VMs with similar SLAs, RPOs, or RTOs have to be grouped by data store. Array-based replication will typically replicate at a data store level or at a group of data stores. And that means that we have to group VMs in with similar requirements together in order to have them replicated in a similar fashion. This could have an impact on storage efficiency, meaning that storage efficiency could be negatively impacted because we have VMs that have to be grouped in certain ways and we can't place them in the most ideal way for storage efficiency. Here's another example. Some VMs will run Windows Server 2003 to support older workloads. Although many organizations are transitioning to Windows Server 2008, there is still quite a bit of Windows Server 2003 out there. And in this particular case, what this means is that when we install Windows Server 2003 into a virtual machine, if we don't perform alignment, and this is the design impact listed here, VMDKs are going to have to be manually aligned. If we don't perform alignment, then our Windows file system will be misaligned on the VMDK and can in some cases, create a significant storage penalty. Now, Windows Server 2008 addresses that and aligns itself properly. And that's why this example shows Windows Server 2003. But that means, as a risk, you have to build the alignment into your VM templates, or you have to have additional operational complexity to fix that, which can result in downtime or other outages in order to fix misalignment. Here's a last example before we wrap up the lesson. VMs are going to run software array to provide redundancy across physical arrays. Perhaps the physical arrays aren't as redundant as the organization requires, but in some case we're going to use software RAID to provide redundancy. So we're going to have multiple VMDKs sitting on different physical systems, and we're going to mirror them across. Well, that means additional resources, additional host CPU, additional RAM, additional storage, and storage connectivity are going to be required in order to satisfy this design decision. And that means that the ability of design to meet certain capacity or growth goals could be compromised in that we have to allocate additional resources to account for this extra level of availability, and therefore we can't grow as much as we may have initially anticipated. As we wrap up this lesson then, let's take a quick look at what we covered. We first started out with a discussion of fitting VM configuration into the design, looking at how VMs and the requirements of VMs affect the design or the rest of the design, and how the rest of the design affects what we can and cannot do within VMs. From there, we moved into a discussion of three aspects of VM configuration. First, allocating resources to VMs like RAM, storage, CPUs, other resources. We then looked at configuring VMs to support the various availability techniques and making sure that if we do require certain availability mechanisms in place, that the VMs are ready to support those. Following that, we had a discussion on deploying VMs and some of the design considerations that need to be accounted for. And finally, we looked at analyzing for design impact. This is part of our ongoing effort to maintain a holistic view and continue to understand the relationships and the dependencies between the various parts of the design. That's it for this lesson. Thanks for watching.